The morning of January 16th, 1943, dawned cold and still over Portland, Oregon. At the Swan Island shipyard, the air temperature hovered just above freezing, and a thin crust of frost coated the metal fittings along the fitting-out dock. The SS Schenectady, a brand-new T2 tanker fresh from her sea trials, sat moored peacefully in calm water, her hull gleaming with recent paint. She had been completed just 16 days earlier, a marvel of modern shipbuilding speed. Her keel had been laid on July 1st, 1942. By late October, she'd been launched, and by the end of December, she'd been declared ready for service, a testament to Henry Kaiser's revolutionary assembly line shipbuilding methods. At 10:30 in the evening, without warning, a sound like a thunderclap shattered the winter quiet. Workers more than a mile away heard it clearly, a sharp metallic crack that echoed off the Willamette River and bounced between the industrial buildings lining the waterfront. Those closest to the dock felt the concussion in their chests, a physical blow that stopped conversations mid-sentence and sent men running toward the fitting-out pier. What they found defied comprehension. The Schenectady's hull had cracked almost completely in half just aft of her superstructure. The fracture ran down both port and starboard sides, reaching nearly to the keel. The bottom plates had held, but the keel itself had fractured and jackknifed upward, lifting the ship's midsection clear out of the water while her bow and stern sagged toward the river bottom. The tanker hung there in the darkness like a grotesque metal butterfly, her back broken, her spine exposed to the winter air. No storm had struck her, no explosion had torn through her hull, no torpedo had found her side. The Schenectady had simply cracked in two while sitting peacefully at the dock, for no apparent reason anyone could see. Within hours, Coast Guard engineers swarmed over the wreck, searching for answers. Their initial conclusion seemed obvious. The welds must have been faulty. The workers, many of them women with only weeks of training, must have made mistakes. The revolutionary all-welded construction Henry Kaiser championed must have been pushed too far, too fast. But the Schenectady was not alone. She was simply the most dramatic example of a crisis that had been building since the first Liberty ships began crossing the North Atlantic 2 years earlier. A crisis that would eventually claim 19 ships that broke completely in half, caused nearly 1,500 instances of serious structural failure, and force American engineers to confront fundamental truths about steel, temperature, and the limits of innovation driven by wartime desperation. The story of how one solution, dismissed by many as backwards thinking, would save thousands of lives, begins not with that spectacular failure in Portland, but 18 months earlier, in the desperate spring of 1941, when Britain stood alone against Nazi Germany, and merchant ships were dying faster than they could be replaced. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. In March of 1941, German U-boats were winning the Battle of the Atlantic. Winston Churchill would later write that the U-boat peril was the only thing that truly frightened him during the war. The mathematics were brutal and simple. British shipyards could build perhaps one merchant ship per month. German submarines were sinking ships by the dozens. At that rate, Britain would starve before she could fight. The British had a solution, though it was hardly elegant. A simple, sturdy design based on an old tramp steamer called the Empire Wind. The ship used an obsolete triple expansion reciprocating steam engine, the kind of power plant that hadn't been cutting-edge technology since before the First World War. But triple expansion engines had two critical advantages. They were simple enough that dozens of companies could manufacture them, and they didn't require the precision machining or scarce materials that modern steam turbines demanded. The British brought their plans to America in early 1941, months before Pearl Harbor would force America into the war. The American firm Gibbs and Cox modified the design, for American shipyards, making one critical change that would echo through the years to come. Where the British design called for traditional riveted construction, the American version would be welded. Riveting had been the standard method of shipbuilding for decades. Steel plates were overlapped and joined with red-hot rivets driven through aligned holes, creating joints that were strong, reliable, and well understood. But riveting was slow. Each rivet required a team of workers, a heater to bring the rivet to cherry red temperature, a catcher to receive it with tongs, a bucker-up to hold a heavy dolly bar against the rivet head, and a riveter to drive the rivet home with a pneumatic hammer. A single Liberty ship would have required hundreds of thousands of rivets, and riveters were skilled workers who took years to train properly. Welding promised revolution. Two steel plates could be joined edge to edge with an electric arc, creating a continuous seam without overlapping material. The process was faster, used less steel, and could be performed by workers trained in a matter of weeks rather than years. Arc welding had been used on some German pocket battleships in the 1930s, where it saved 1,000 tons of weight per ship, but no one had ever attempted to build merchant ships entirely by welding, and certainly not at the scale America was proposing. President Franklin Roosevelt announced the Emergency Shipbuilding Program in September of 1941. The goal seemed impossible. America would build a fleet of standardized cargo ships using assembly line techniques borrowed from automobile manufacturing. The ships would be built from prefabricated sections welded together, with construction times measured in weeks rather than months. The first 14 ships were launched on September 27, 1941, in ceremonies Roosevelt called Liberty Fleet Day. He quoted Revolutionary War hero Patrick Henry's famous declaration, "Give me liberty or give me death." When the president said these ships would bring liberty to Europe, the name stuck. They became Liberty ships. The design was designated EC2SC1. The EC stood for Emergency Cargo. Each ship would be 440 feet long, 57 feet wide, capable of carrying over 9,000 tons of cargo. The holds could swallow 2,800 jeeps, or 440 tanks, or 230 million rounds of rifle ammunition. On deck, locomotives and aircraft could be lashed down for transport. 18 shipyards across America prepared to build them. From New England to the Gulf Coast, from the Atlantic to the Pacific, Kaiser and other industrialists constructed massive facilities capable of assembling ships like automobiles. Henry Kaiser, who had never built a ship in his life before 1940, brought techniques from his dam-building projects: prefabrication, modular construction, competition between work crews. On the Grand Coulee Dam, Kaiser had split the workforce in two and made them race to complete their sections of the spillway first. He brought that same competitive spirit to shipbuilding. The early ships took time to build. The SS Patrick Henry, the first Liberty ship launched, required 244 days from keel laying to completion. But as workers gained experience and methods improved, construction times plummeted. By late 1942, the average construction time had fallen to 45 days. Kaiser's yards were completing ships in less than 3 weeks from keel to launch. In November 1942, one crew set a record that would never be broken. They built the SS Robert E. Peary in 4 days, 15 hours and 30 minutes from keel laying to launch. The record was partly a publicity stunt. Much fitting-out work remained after the launch, but it demonstrated what mass production and welding made possible. By 1943, American shipyards were launching 3 Liberty ships every single day. The arsenal of democracy was producing vessels faster than U-boats could sink them. For the first time since the war began, the mathematics of the Battle of the Atlantic shifted in favor of the Allies. But even as production soared, disturbing reports began filtering back from the North Atlantic. Ships were developing cracks, not small stress cracks that could be repaired, but massive fractures that split steel plates like paper. In January of 1943, about 20 ship failures occurred. Some suffered what would later be classified as Class 1 damage, fractures that endangered the ship or resulted in its loss. The Schenectady's spectacular break in Portland was just the most visible example. Then came March 5th, 1943. The Liberty ship Thomas Hooker broke in half in heavy weather in the North Atlantic. 2 days later, on March 7th, the JLM Curry split apart in very high seas in the Greenland Sea. On March 29th, the SO Manhattan cracked in clear weather, while in Ambrose Channel, calm water just outside New York Harbor. Like the Schenectady, she hadn't even encountered rough seas. She simply fractured while going about routine operations. The pattern became impossible to ignore. Ships were failing under conditions that shouldn't have stressed them severely. Some broke in storms, true, but others cracked in calm water, or at dock, or during routine loading operations. The SS John P. Gaines broke in half on November 24, 1943, taking 10 men with her. The Valery Chkalov split during a heavy storm in the North Pacific on November 11th. Throughout the winter of 1943 to 1944, the casualty rate climbed steadily higher. Coast Guard engineers and Maritime Commission officials scrambled to understand what was happening. The obvious suspect was welding. Perhaps the hastily trained workers were making mistakes. Perhaps the new electric arc welding techniques were fundamentally unsuitable for ship construction. Perhaps Henry Kaiser's revolutionary methods had been pushed too far, sacrificing quality for speed. Welding inspectors began examining every seam on damaged ships. They found flaws, certainly. Hastily trained welders working under immense time pressure had created welds with porosity, slag inclusions, and incomplete penetration. But many of the fractures didn't even start at welds. The cracks ran straight through solid steel plate, bypassing welded seams entirely. The fractures seemed to originate most commonly at square corners of cargo hatches, places where the ship's design created stress concentrations. But stress concentrations alone couldn't explain the catastrophic nature of the failures. Merchant mariners who sailed Liberty ships developed an uneasy relationship with their vessels. The ships were needed desperately. Without them, supplies couldn't reach Britain, couldn't reach the Soviet Union through the dangerous Murmansk run, couldn't support the island-hopping campaign across the Pacific. But every crew member who walked up a Liberty ship's gangway wondered if this voyage would be the one where the hull cracked open beneath their feet. The statistics were sobering. 1 in 26 merchant mariners died during the war, a higher fatality rate than any branch of the armed forces. Submarines, mines, aircraft, and kamikaze attacks all took their toll. But the knowledge that the ship itself might simply break apart added another layer of terror to an already dangerous occupation. Some captains took to routing through calmer waters whenever possible, avoiding the roughest seas and the coldest temperatures. But convoy routes were determined by strategic necessity, not by the preferences of nervous captains. Lieutenant Commander Malcolm Henderson, a naval architect assigned to the Maritime Commission in Washington, spent the winter of 1943 to 1944 studying failure reports. Henderson had degrees from MIT and had worked in commercial shipbuilding before the war. He understood naval architecture, understood stress analysis, understood metallurgy better than most. What he was seeing in the failure reports didn't make sense, according to conventional engineering wisdom. The steel used in Liberty ships was standard shipbuilding grade. It had been used successfully in riveted ships for decades. The plates passed standard tensile strength tests. The material properties looked adequate on paper. Yet, in service, the steel was failing in ways that suggested brittleness rather than ductility. In his office, overlooking the Potomac River, Henderson laid out photographs of failed ships. The fracture surfaces were clean, almost glassy in appearance. There was no necking, no plastic deformation visible. The steel had simply snapped, like glass or cast iron, rather than like ductile structural steel. He pulled meteorological data for the dates of each failure. The pattern jumped out immediately. The vast majority of catastrophic failures occurred during winter months. Many happened when air temperatures were near or below freezing. Ships operating in the North Atlantic during winter faced water temperatures that could drop to just above the freezing point of salt water, around 29 degrees Fahrenheit. Those same ships faced air temperatures that could plunge well below zero during Arctic storms. Henderson knew that steel's properties changed with temperature. All engineers knew that, but the conventional wisdom held that structural steel remained ductile down to temperatures far below anything encountered in normal service. What if that conventional wisdom was wrong? What if the grade of steel being used in Liberty ships had a ductile to brittle transition temperature much higher than anyone realized? He picked up the phone and called Cambridge University in England. He needed to speak with someone who understood the fundamental behavior of steel at the atomic level, someone who could explain how solid metal could behave like glass. The person he needed was Constance Tipper, though he didn't know her name yet. She would provide the answer that everyone had been searching for, but her solution would only explain half the problem. The other half, the reason welded ships failed so catastrophically when their steel became brittle, would require a different kind of thinking. It would require looking backward to supposedly obsolete technology, accepting that progress sometimes meant combining old methods with new ones, and it would require shipyard workers to do something that seemed absurd to engineers focused on speed and efficiency. They would have to slow down, do extra work, and install rivets in ships that were supposed to be all welded. The winter of 1944 brought the crisis to its peak. January was brutal. 20 Class 1 failures occurred that month alone. Ships cracked, split, or suffered damage severe enough to threaten their survival. The Maritime Commission temporarily considered withdrawing Liberty ships from troop transport duty, though military necessity made that impossible. Too many troops needed transport. Too many supplies had to reach Europe in preparation for the invasion everyone knew was coming. Then March arrived, and with it came 120 failures. The number was staggering, unprecedented. More than one ship every day was suffering serious structural damage. The rate of Class 1 casualties, fractures that endangered ships or resulted in their loss, had climbed to 4.3 per 100 ship years for the original design. Before the war, the loss rate from all causes for merchant ships had been 1 per 100 ship years. Liberty ships were failing structurally more than 4 times as often as conventional ships failed from all causes combined, including enemy action. Across the Atlantic, in Cambridge, England, Constance Tipper worked methodically through the problem. Tipper was no ordinary researcher. She had earned her doctorate in metallurgy from Cambridge in 1921, when women in science faced barriers that would have stopped most. She had spent 2 decades studying the mechanical properties of metals, developing testing methods that could reveal how materials behaved under stress. When the Ministry of War Transport brought her a plate of steel from the Empire Duke, a failed Liberty ship built in Britain, she knew exactly how to approach the mystery. She began with the assumption that everyone else had made. Perhaps the fractures started in the welds. Perhaps the welding process itself damaged the steel, creating zones of weakness where cracks could initiate. She examined weld seams microscopically, looking for heat-affected zones, looking for changes in grain structure, looking for anything that would explain catastrophic failure. The welds showed flaws, certainly. Hastily made field welds rarely matched the quality of carefully controlled laboratory welds, but the flaws weren't severe enough to explain the failures. Then Tipper did something simple but crucial. She tested the steel at different temperatures. She took samples of the Liberty shipplate steel and subjected them to impact testing, measuring how much energy the material could absorb before fracturing. At room temperature, the steel performed adequately. It showed decent toughness, absorbed reasonable amounts of impact energy. But as she lowered the temperature, something dramatic happened. At around 40 degrees Fahrenheit, the steel's behavior changed fundamentally. Above that temperature, it behaved like normal ductile steel, bending and deforming before breaking. Below that temperature, it became brittle, shattering like glass, with almost no plastic deformation. The transition wasn't gradual. It was sharp, dramatic, a cliff edge in the material's properties. Tipper had discovered the ductile to brittle transition temperature for Liberty ship steel, and it was far, far higher than anyone had expected, 40 degrees Fahrenheit. That was the critical threshold. Ships operating in the North Atlantic during winter routinely encountered temperatures below that. The steel in their hulls was spending months at a time in a brittle state, vulnerable to fracture from even modest stress levels. When a wave struck the bow, when cargo shifted during a roll, when thermal stresses developed as the sun warmed the deck while the hull remained cold, the brittle steel simply snapped. Tipper's discovery explained why the ships were failing. It explained the winter concentration of failures. It explained why fractures showed no plastic deformation. The steel wasn't failing because it was defective. It was failing because it was being used at temperatures where its fundamental behavior changed. In riveted construction, this same steel had worked fine because riveted ships had a built-in protection against brittle fracture. When a crack started in a riveted ship, it would propagate through a plate until it reached the edge. There, the crack encountered a rivet line, a joint where two plates overlapped and were held together by rows of rivets. The crack couldn't easily jump across that discontinuity. The overlapping plates, the holes drilled for rivets, the mechanical joint itself, all acted as barriers to crack propagation. A crack might split one plate, but it would likely stop at the rivet line. The ship would need repair, but it wouldn't catastrophically fail. Welded ships had no such protection. The welded seams created essentially continuous plates of steel stretching the entire length of the hull. When a crack started in brittle steel, it could propagate unimpeded for dozens of feet, even hundreds of feet, until it encountered something that stopped it. Square hatch corners where stress concentrated provided ideal starting points. Once a crack began, it raced through the brittle steel at nearly the speed of sound, zipper-like, splitting the hull open. The solution seemed obvious in retrospect, though it would take months to implement fully. If welded ships needed the crack-stopping properties of riveted construction, then welded ships should have riveted elements deliberately incorporated into their structure, not rivets everywhere that would defeat the speed advantages of welding, but strategic rivet lines placed where they could arrest cracks before they became catastrophic. In April of 1944, the Maritime Commission issued new specifications. Liberty ships under construction and ships already in service would be retrofitted with riveted seam straps. At minimum, 4 riveted seams would run the length of each hull, positioned where they could intercept cracks propagating from the most common failure points. The riveted straps were steel bands, running longitudinally along the hull, attached not with welds, but with rows of rivets driven through pre-drilled holes. The modification was not popular with shipyard managers focused on production speed. Installing rivets meant bringing back riveting gangs, meant additional labor hours per ship, meant slowing down the production lines that had become so gloriously efficient. Henry Kaiser's yards had perfected the art of rapid welding. Now they were being told to go backwards, to add old-fashioned riveted joints to their modern all-welded ships. But the mathematics of survival were undeniable. Without the modification, Liberty ships had a Class 1 casualty rate of 4.3 per 100 ship years. After the riveted crack arresters were installed, that rate dropped to 0.5 per 100 ship years. The riveted seams were working. Cracks still occurred, ships still suffered damage, but the catastrophic failures dropped dramatically. The square hatch corners were redesigned as well, rounded to reduce stress concentration. Steel quality was improved slightly, though wartime constraints limited how much the metallurgy could be changed. Ships were routed through calmer, less icy waters whenever possible, but the riveted crack arresters were the critical fix, the simple, elegant solution that combined old technology with new methods to save the program. Chief Petty Officer Thomas Morrison had spent 23 years in the merchant marine before the war. He'd worked on riveted ships his entire career, from small coastal freighters to the great Atlantic liners. When the war started and he joined the maritime service, he found himself assigned to train the new generation of shipyard workers who were flooding into Kaiser's yards. Morrison remembered standing in a Richmond, California shipyard in May of 1944, watching a riveting gang install crack arrestor straps on a Liberty ship that had already been launched but not yet commissioned. The ship sat in a fitting-out berth, her hull complete, her decks finished, but now she was being modified with these strange retrofits that everyone was talking about. The riveting gang was good. Morrison could see that immediately. The heater worked his portable forge, bringing rivets to the proper cherry-red temperature. The catcher stood ready with his tongs, positioned on the opposite side of the steel plate. The bucker-up held his heavy dolly bar firm against the rivet head, and the riveter positioned his pneumatic hammer, a tool that weighed 40 pounds and hammered with the force of hundreds of impacts per minute. When a rivet was passed, still glowing red, the catcher grabbed it with his tongs and slammed it into the pre-drilled hole. The rivet's shank filled the hole instantly. The bucker-up pressed his dolly bar tight against the formed head on one side, and the riveter drove his hammer against the protruding shank on the other side, smashing the hot metal into a second head, creating a permanent mechanical joint that would hold the steel plates together under enormous stress. The noise was tremendous, a rapid-fire percussion that echoed across the shipyard. Sparks flew where hot metal met steel. The smell of hot iron filled the air. It was old technology, pre-war technology, technology that the welding revolution was supposed to have made obsolete. Yet, here it was, being carefully installed in the most modern ships America had ever built, because old technology turned out to have properties that modern methods couldn't match. "Seems backwards, doesn't it?" Morrison said to the young supervisor standing next to him. The supervisor, a college-educated naval architect, maybe 25 years old, nodded slowly. "The whole point of these ships was to weld them fast. Now we're going back to rivets. Some of the efficiency experts are furious about it." Morrison spat tobacco juice over the side of the dock. "Efficiency experts don't sail in winter storms in the North Atlantic. I do, and I can tell you, I'd rather have a ship that takes an extra week to build but doesn't crack in half when the temperature drops." The young supervisor didn't argue. He'd seen the photographs of the Schenectady, the John P. Gaines, the dozens of other ships that had split open. He'd read the casualty reports, the statistics about how many men were lost when ships broke up at sea. Speed mattered, production numbers mattered, but none of it mattered if the ships didn't survive their first winter convoy. The riveting gang worked methodically down the ship's length. They would install 4 complete crack arrestor straps on this vessel, running from bow to stern, positioned where engineering analysis predicted they would intercept the most likely crack paths. Each strap required hundreds of rivets. Each rivet required several minutes to install properly. The work would take days, adding time to the ship's completion schedule, slowing down the production metrics that Kaiser tracked so carefully. But the physics were undeniable. The riveted seams created discontinuities in the hull structure, barriers that cracks couldn't easily cross. When brittle steel fractured during cold weather operations, the crack would race through the welded plates until it hit a rivet line. There, the crack would either stop completely or require significantly more energy to propagate further. In most cases, the crack stopped. The ship suffered damage, yes, but localized damage that could be repaired rather than catastrophic failure that could sink the vessel. Captain Richard Hayes commanded a Liberty ship called the Samuel Chase, one of the early vessels, modified with crack arrestor straps in late 1944. The Chase had been built in September of that year in Baltimore, and Hayes took command of her in October, just as the winter convoy season was beginning. His cargo holds were loaded with ammunition, field artillery, and medical supplies destined for Antwerp to support the Allied armies pushing into Germany. The crossing began on November 8, 1944, as part of convoy HX 318, 43 merchant ships escorted by destroyers and corvettes. The North Atlantic was entering its most dangerous season when German U-boats found perfect hunting conditions in the long winter darkness and when the weather itself became as deadly as any enemy weapon. 4 days out from New York, the convoy ran into a storm system that would have been remarkable even by North Atlantic standards. Wind speeds climbed past 50 knots, waves built to 40 feet, grey-green mountains of water that towered above the ship's bows before crashing down on foredecks with impact forces measured in tons per square foot. The air temperature dropped to 26 degrees Fahrenheit. The water temperature hovered around 33 degrees. Hayes stood on the Samuel Chase's bridge, wedged into a corner to keep his balance as the ship pitched and rolled. He'd been at sea for 30 years, had weathered hurricanes in the Caribbean and typhoons in the Pacific. This storm ranked among the worst he'd experienced. Around him, the convoy was scattering. Ships were falling behind, unable to maintain station in the mountainous seas. Somewhere in the darkness, 2 freighters had collided during a confused maneuver, though Hayes had only heard about it over the radio. At 0330 hours on November 13th, Hayes felt something he'd never felt before. Not an impact, not an explosion, but a sharp vibration that ran through the entire ship, a shudder that suggested something structural had given way. His first thought was that they'd struck a mine or been torpedoed. But there had been no explosion, no column of water thrown up by a detonation. He sent his first mate to investigate. The man returned 15 minutes later, his face pale in the bridge's red night lighting. "Captain, we've got a crack. Forward hold, port side, starting at the number 2 hatch. It runs down about 20 feet, right through the hull plating." Hayes felt his stomach drop. He'd read the reports about Liberty ships breaking in half. Every captain had read those reports. The question now was whether his ship would be one of them, or whether she would survive long enough to reach port. "Is water coming in?" Hayes asked, keeping his voice steady. "Some seepage through the crack, but the pumps are handling it. The crack stopped at one of those riveted straps they installed. It just stopped dead, like it hit a wall." Hayes felt something release in his chest. Tension he hadn't even realized he was carrying. The crack had stopped. The riveted crack arrestor strap had done exactly what it was designed to do. The Samuel Chase had suffered damage that, in a fully welded ship, might have propagated the entire length of the hull. Instead, the crack had run 20 feet and stopped cold when it hit the riveted seam. They limped into Liverpool on November 21st, 1944, 8 days behind the rest of the convoy, but afloat. British shipyard workers swarmed over the crack, documenting it, photographing it, measuring it. The crack was clean, brittle, showing no plastic deformation. It had raced through the steel plate until encountering the riveted strap, where the crack tip had run into the discontinuity created by the overlapping plates and rivet holes. Unable to propagate further without significantly more energy, the crack had simply stopped. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Hayes wrote a detailed report for the Maritime Commission when he returned to the United States in January of 1945. His account was added to hundreds of similar reports from other captains who had experienced cracks that stopped at riveted straps. The empirical evidence was overwhelming. The modification worked. Ships were surviving damage that would have killed them before the crack arresters were installed. The statistical analysis compiled by the Maritime Commission in 1946 told the full story in numbers. Of the 2,710 Liberty ships built during the war, approximately 1,500 suffered some form of brittle fracture. But after the crack arrestor modifications were implemented in mid-1944, the rate of catastrophic failures dropped by nearly 90%. Ships still developed cracks, especially during winter operations in cold waters, but those cracks rarely propagated to the point of total hull failure. The T2 tankers, which used similar all-welded construction, told a parallel story. Without crack arresters, T2 tankers had a Class 1 failure rate of 1.9 per 100 ship years. After riveted seams were added, that rate dropped to 1.2 per 100 ship years. The improvement was significant, though not as dramatic as with the Liberty ships, possibly because tankers faced different stress patterns from their liquid cargo loads. The Victory ships, designed as improved Liberty ship replacements, beginning in 1944, incorporated the lessons learned from the cracking crisis. Victory ships used better steel with improved low-temperature toughness. They featured wider frame spacing, 36 inches, instead of the Liberty's 30 inches, making the hulls less stiff and better able to flex under stress, and they included crack arrestor features designed into the structure from the beginning, rather than retrofitted afterward. But even as the modifications saved lives and ships, the fundamental problem remained unsolved. The steel Liberty ships used simply wasn't suitable for the conditions they encountered. At temperatures below 40 degrees Fahrenheit, the material became brittle, vulnerable to catastrophic fracture. No amount of careful welding, no degree of quality control could change that basic metallurgical reality. After the war, the Liberty ship crisis became a foundational case study in materials science and fracture mechanics. Universities taught courses using Liberty ship failures as examples. Engineering textbooks devoted chapters to the brittle fracture problem. Constance Tipper's work on ductile to brittle transition temperatures became fundamental knowledge that every materials engineer had to understand. The disaster also drove metallurgical research. Steel manufacturers developed new grades of steel with much lower transition temperatures, alloys that remained ductile even in Arctic conditions. Modern ship steel is guaranteed to maintain toughness at temperatures far below anything a Liberty ship steel could handle. Testing protocols changed as well. The Charpy impact test, which measures a material's toughness at different temperatures, became mandatory for structural steels used in critical applications. Design practices evolved too. Engineers learned to avoid sharp corners and stress concentrations in structures. The square cargo hatch corners that contributed to so many Liberty ship failures became a textbook example of what not to do. Modern ships feature rounded corners, generous radii, and careful attention to stress flow throughout the structure. And the concept of crack arrest, using structural discontinuities to stop crack propagation, became a standard design consideration. Yet, the Liberty ships themselves, despite their flaws, were considered a war-winning weapon. Between 1941 and 1945, American shipyards built 2,710 Liberty ships, easily the largest number of ships ever produced to a single design. They transported millions of tons of cargo, carried hundreds of thousands of troops, and supplied Allied armies on every front. Approximately 200 Liberty ships were lost to enemy action, weather, accidents, and structural failure combined. But more than 2,500 survived the war. After 1945, many Liberty ships continued in service. Greek shipping magnates, including Aristotle Onassis and Stavros Niarchos, built their post-war shipping empires by buying surplus Liberty ships at bargain prices. 526 Liberty ships went to Greek owners, 98 went to Italian companies. The ships that had been designed for a 5-year service life in emergency conditions ended up sailing commercial routes for decades. The SS John W. Brown and the SS Jeremiah O'Brien survive today as museum ships, the only 2 Liberty ships still in operational condition. The John W. Brown, built in Baltimore and launched in September of 1942, sails regularly from her home port in Baltimore, carrying passengers who want to experience what merchant mariners endured during the war. During the ship's restoration in the 1980s, approximately 15,000 rivets were replaced, most from underwater portions of the hull where corrosion had taken its toll over 40 years. Those replacement rivets, driven by hand using the same techniques Morrison watched in 1944, connected the present directly to the past. The modern riveting crews used the same tools, followed the same procedures, created the same mechanical joints that had saved Liberty ships from catastrophic failure during the war. The act of driving those rivets was a reminder that sometimes progress isn't linear, that sometimes the old ways combine with new methods to create solutions that neither approach could achieve alone. The story of Liberty ships and crack arresters resonates because it challenges assumptions about technological progress. The narrative everyone wanted in 1941 was simple and compelling. Old, riveted construction was slow and expensive. New, welded construction was fast and efficient. Progress meant abandoning old methods for new ones, moving forward without looking back. But reality proved more complicated. Welded construction was indeed faster and more efficient, but welding created vulnerabilities that riveted construction had inadvertently protected against. The solution wasn't to abandon welding and return entirely to riveting. The solution was to combine both methods, using welding for speed and efficiency, while incorporating riveted elements where they provided critical crack arrest capability. Lieutenant Commander Henderson, the naval architect who had first noticed the temperature correlation in failure data, wrote a memo to the Maritime Commission in June of 1945. As the war in Europe ended and attention turned to the continuing fight against Japan. In that memo, he reflected on the lessons learned from the Liberty ship crisis. "We believed we were innovating," Henderson wrote. "We believed that welding represented progress, that riveting represented the past, and that progress meant leaving the past behind. What we learned, at great cost, was that innovation often means combining the best of old and new, that progress sometimes requires going backward to go forward, and that the most important question isn't whether a technology is modern or obsolete, but whether it works." Henderson's memo ended up filed away in Maritime Commission archives, one document among thousands, but his insight captured something essential about the Liberty ship story. The ships succeeded not because they were entirely modern, and not because they returned to old methods, but because they learned to integrate both. The welding provided speed, the rivets provided safety. Together, they created a system that worked well enough to help win the war. The men who sailed Liberty ships through North Atlantic winters understood this in ways that engineers sitting in offices could not. They didn't care whether their ship was built with cutting-edge technology or obsolete methods. They cared whether the hull would hold together when 40-foot waves crashed over the bow and the temperature dropped below freezing and the steel around them entered that brittle state where it might crack at any moment. Captain Hayes, who had commanded the Samuel Chase when she cracked during that November storm in 1944, continued sailing Liberty ships through the end of the war. He commanded 3 different vessels between November 1944 and August 1945, carrying cargo across the Atlantic, through the Mediterranean, and eventually to the Pacific for the final push against Japan. In all 3 ships, he checked the riveted crack arrestor straps regularly. He would walk the length of the hull, running his hand along the rivet lines, feeling for any movement or looseness that might indicate a problem. The rivets were ugly, he thought. They broke up the clean lines of the welded hull. They represented a step backward in construction efficiency. But they also represented the difference between his ship making it home and his ship breaking in half at sea. Hayes survived the war and returned to commercial shipping. He commanded merchant vessels through the 1950s and into the 60s, eventually retiring in 1967 after 40 years at sea. In his retirement, he occasionally gave talks to maritime history societies about his wartime service. Inevitably, someone would ask him about the Liberty ship cracks, about what it felt like when the Samuel Chase fractured in mid-Atlantic. "I thought we were done," Hayes would say. "I thought the crack would run the whole length of the ship and she'd break up before we could even get the lifeboats away." But then my mate came back and told me the crack had stopped at one of those riveted straps, and I realized that some engineer somewhere had actually thought about what happens when things go wrong, had actually planned for failure and built in a way to contain it. Hayes would pause then, looking at his audience. That's what I remember most, not the crack itself, but the fact that someone had anticipated it. Someone had looked at the welded ships breaking up and figured out how to make them survive. That's engineering. Not building something perfect, but building something that works even when things go wrong. The Liberty ship program built 2,610 vessels in 4 years. the program suffered approximately 1,500 instances of brittle fracture, 19 catastrophic hull failures, and hundreds of lives lost to structural failures. But the program also adapted, learned, and implemented fixes that reduced failure rates by 90% once the problems were understood. In the cold calculus of war, that counted as success. Modern ship design owes much to those failures. Every merchant ship afloat today benefits from the metallurgical research sparked by Liberty ship cracks. Every structural engineer learns about stress concentrations and crack arrest, partly because Liberty ships taught those lessons in the most dramatic way possible. And every time a designer incorporates redundancy or protective features into a structure, the ghost of those riveted crack arresters is present in their thinking. But perhaps the deepest lesson from the Liberty ship crisis is about humility in the face of nature's laws. The engineers and industrialists who designed the all-welded Liberty ships weren't foolish. They were brilliant men solving impossible problems under crushing time pressure. They innovated genuinely, creating production methods that revolutionized shipbuilding. Their welding techniques did make it possible to build ships faster than ever before in history. What they hadn't accounted for was something fundamental about how materials behave at different temperatures, something that wasn't well understood in the 1940s. The ductile to brittle transition temperature wasn't a secret, but its implications weren't fully appreciated. Engineers knew steel behaved differently at very low temperatures, the kind of temperatures encountered in Arctic exploration. They didn't realize that the transition could occur at temperatures as mild as 40 degrees Fahrenheit, temperatures encountered routinely in North Atlantic winter operations. Constance Tipper's work changed that forever. After she published her findings about the Liberty ship steel's transition temperature, materials testing protocols changed worldwide. The Charpy impact test, which she used to measure toughness at different temperatures, became standard practice. Steel manufacturers began guaranteeing low-temperature toughness properties, and designers began paying attention to the operating temperature range when selecting materials. In the decades after World War II, steel metallurgy advanced dramatically. Modern ship steels maintain excellent toughness down to temperatures of minus 40 degrees Fahrenheit or lower, temperatures far below anything Liberty ship steel could handle. The chemical composition is carefully controlled to minimize impurities like sulfur that increase brittleness. Heat treatment processes create fine-grained microstructures that resist crack propagation. Testing is rigorous, with every batch required to meet strict toughness standards at specified temperatures. But even with vastly improved materials, modern ships still incorporate crack arrest features. Passenger ships have watertight bulkheads spaced at regular intervals, creating compartmentalized structures that can contain damage. Cargo ships feature longitudinal and transverse stiffeners positioned to stop crack propagation. Naval vessels include blast protection features designed to limit damage from weapons hits. The principle established by Liberty ship crack arresters that structures should be designed to contain failure rather than merely prevent it has become fundamental to modern engineering. The 1960s and 70s saw a series of structural failures in large cargo ships and tankers that echoed the Liberty ship problems. The SS Marine Electric broke up in 1983, killing 31 of her 34 crew members. Investigation revealed that her aging hull had developed cracks that propagated catastrophically in cold weather off the coast of Virginia. The Daniel J. Morrell, a Great Lakes ore carrier, broke in half during a storm in 1966, with only one survivor from her crew of 29. These failures reinforced the lessons from World War II that brittle fracture remains a threat whenever vulnerable steel encounters cold temperatures and high stress. In 1989, the supertanker Exxon Valdez ran aground in Prince William Sound, Alaska, spilling 11 million gallons of crude oil. While the grounding itself was the primary cause, the extensive hull damage that allowed the oil to escape was made worse by cold temperature embrittlement of the aging steel. Modern double-hull tanker designs incorporate better steel and crack arrest features, specifically to contain damage from groundings or collisions. Lessons learned from a century of structural failures, stretching back through the Exxon Valdez to the Liberty ships and beyond. The veterans who served on Liberty ships during World War II rarely talked about the structural problems. Their stories focused on U-boats, on kamikaze attacks, on storms and convoy battles, and the grinding exhaustion of wartime service. The risk that their ship might simply crack apart was just one more danger in an environment saturated with threats. They adapted to it the way people adapt to any chronic risk, by not thinking about it too much and by maintaining faith in their ships and shipmates. But some veterans, in their later years, reflected on what the experience had taught them about technology and progress. Merchant mariner John Peters sailed on 7 different Liberty ships between 1942 and 1945, serving as an able seaman and eventually as a boatswain. After the war, he worked in shipyards as a supervisor, helping to build the container ships and supertankers that would dominate post-war merchant shipping. In an oral history recorded in 1997, when Peters was 79 years old, he talked about watching welders work on a modern ship and thinking about those riveted crack arrestor straps from half a century earlier. "The young guys today, they think welding is just how you build ships," Peters said. "They don't know there was a time when we thought welding was going to kill us all. And maybe it would have if someone hadn't figured out to add those rivet lines." The interviewer asked if he'd been scared, sailing on ships that might crack apart. Peters laughed. "Scared? Hell, I was terrified. But we were all terrified. Of U-boats, of mines, of the weather, of everything. The ship cracking was just one more thing to worry about. You didn't let it stop you. The cargo had to get through. The war had to be won. So you sailed. And you hoped the engineers knew what they were doing with those rivet fixes, and you trusted your ship. That trust was perhaps the most remarkable aspect of the story. After the Schenectady's spectacular failure, after news of ships breaking in half spread through the merchant marine, sailors still crewed Liberty ships. They still crossed the North Atlantic in winter. They still carried ammunition and aviation fuel and troops into combat zones. Some of that was patriotic duty, certainly. Some was the simple need for employment during wartime. But some was genuine faith that the problems would be solved, that the engineers would figure out what was wrong and fix it. And the engineers did figure it out. Not quickly enough to prevent all failures, not elegantly enough to avoid hundreds of cracks and dozens of deaths, but they solved the problem well enough that the vast majority of Liberty ships completed their missions and brought their crews home safely. The riveted crack arresters were a crude fix by some standards, a step backward in construction methodology, but they worked, and in wartime, working solutions matter more than elegant ones. The Memorial Day ceremonies at the American Merchant Marine Veterans Memorial in New York regularly honor the merchant mariners who died in World War II. Over 9,000 merchant mariners lost their lives during the war from all causes: enemy action, weather, accidents, and structural failures. Some of those deaths came when Liberty ships broke apart in cold seas, when brittle fractures raced through hulls faster than crews could react, when ships that had survived U-boat packs and kamikaze strikes simply cracked open and sank. Those men died because the steel in their ships couldn't handle the conditions it encountered, because the ductile to brittle transition temperature wasn't understood, because all welded construction allowed cracks to propagate unimpeded. But thousands of other merchant mariners survived precisely because engineers recognized the problem and implemented the riveted crack arrestor solution. Ships cracked but didn't sink. Crews made it to port with damaged vessels. Cargoes reached their destinations. The SS John W. Brown, the museum ship that still sails from Baltimore, carries a brass plaque near her bow listing the major convoy routes she sailed during the war. Murmansk to supply the Soviet Union, North Africa to support Operation Torch, Sicily for the invasion of Italy, Normandy for D-Day supply missions. Each of those routes took her through conditions where brittle fracture was a real threat, where the temperature dropped below 40 degrees and the steel in her hull entered its brittle state. She survived all of it, brought her crews home safe from every voyage, and now serves as a memorial to the 2010 Liberty ships that were built and the men who sailed them. When visitors tour her decks and holds, they can see the riveted crack arrestor straps running along her hull, visible evidence of the modification that saved so many ships. The rivets themselves are unremarkable, just rows of round heads protruding slightly from the steel, but each one represents a small victory over catastrophic failure, a deliberate choice to incorporate old technology into modern construction, because doing so saved lives. The Liberty ship program stands as both triumph and cautionary tale. The triumph was real. American industry built a fleet of cargo ships faster than any nation had ever built ships before, supplied a global war across multiple theaters, and demonstrated industrial capacity that helped defeat the Axis powers. The production numbers alone, 2,710 ships in 4 years, remain unprecedented and likely will never be matched. But the cautionary tale is equally important. The rush to innovate, the pressure to adopt new methods without fully understanding their limitations, the assumption that modern technology is automatically superior to older methods, all of these led to a crisis that cost lives and nearly compromised the entire program. The Liberty ships succeeded ultimately, not because they were entirely modern, but because they learned to combine modern welding efficiency with old-fashioned, riveted crack arrest capability. That lesson echoes across the decades. In aerospace engineering, in civil construction, in software development, in every field where innovation drives progress, the Liberty ship story serves as a reminder. New methods aren't automatically better than old ones. Progress isn't simply about abandoning the past. Sometimes, the best solutions come from thoughtfully combining old and new, from understanding what each approach does well and creating systems that leverage both strengths. The riveted crack arrestor straps were, in their way, absurd. They slowed production. They added complexity. They required bringing back obsolete skills and tools. They represented, by every metric of modern efficiency, a step backward. But they also saved thousands of lives and allowed the Liberty ship program to succeed despite its fundamental materials problem. In the end, that's all that mattered. On cold winter mornings in Baltimore Harbor, when the temperature hovers around 40 degrees Fahrenheit, the same temperature where Liberty ship steel transitions from ductile to brittle, the SS John W. Brown sits quietly at her dock. Her steel hull, now more than 80 years old, has long since been maintained and preserved with modern protective coatings, but those riveted crack arrestor straps remain visible along her length, testament to the day when someone recognized that the old way and the new way could work together. That progress sometimes requires looking backward, and that the most important engineering question isn't whether something is modern or obsolete, but simply whether it works when lives depend on it. The crack that nearly sank Captain Hayes's ship, the Samuel Chase, ran exactly 20 feet before stopping cold at a riveted crack arrestor strap on that November night in 1944. 20 feet of catastrophic, brittle fracture that should have continued propagating the entire length of the hull, dooming the ship and killing her crew. But the crack stopped, and the ship survived, and Hayes brought her into Liverpool 8 days late, but afloat. That margin between catastrophic failure and survivable damage was measured in rows of old-fashioned rivets, driven through overlapping steel plates. It wasn't elegant. It wasn't efficient. It certainly wasn't what the engineers had planned when they designed the first all-welded Liberty ships, but it was exactly what was needed. And in the end, that made all the difference. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.